During this presentation, we have to concentrate on Cauchy's integral theorem. It's known to you. Suppose a function is analytic, it should satisfy the CR equations. According to Cauchy's integral theorem, if f of z is analytic within a domain D, then for any closed curve C inside D, the value of integral f of z dz is 0. This is our Cauchy's integral theorem. If f of z is analytic within a domain D, then for any closed curve C inside the domain, the value of integral f of z dz is 0. To prove this condition, consider a vector field A in 2 dimensions. A equal to I into x plus j into ay. Then the corresponding dr value, that is difference in position vector, is I into dx plus j into dy, since r equal to ix plus jy. According to Stokes' theorem, we can write A dot dr, which is equal to curl A dot ds. This is C, here we have to put S. C is the closed curve, S is the surface developed by this closed curve C. This closed curve is present inside the domain. A dot dr equal to curl A dot ds. Now we have to find out the value of A dot dr. See, A dot dr is ax dx plus ay dy. Instead of a, we have to put I ax plus j ay dot I into dx plus j into dy. A dot dr, that is I dot I is 1, ax dx plus j dot j1 ay dy. I dot j 0, j dot I 0. Then come to the right hand side. Curl A dot ds. The value of curl A is determined with the help of determinant. Is I j k operator dou by dou x, dou by dou y 0. Since A is a 2-dimensional vector field, here ax ay 0. I into, leave this column and this row. Dou by dou y of 0, ay into 0, 0 minus j into, leave this column and this row. Dou by dou x of 0 minus ax into 0, 0. The only contribution is from the unit vector k, that is k into dou ay by dou x minus dou ax by dou y. This is the value of Cauchy. Instead of this Cauchy, we have to put this k unit vector into dou ay by dou x minus dou ax by dou y. Then dot ds. The value of ds is allowed to operate with this Cauchy. We may get dou ay by dou x minus dou ax by dou y. Entire is multiplied by dx dy. This is the value of right hand side, Cauchy dot ds. Now keep this equation as equation 1. The equation 1 is here a dot dr which is equal to ax integral ax dx plus ay dy is contour C, which is equal to, write on this, the surface integral dou ay by dou x minus dou ax by dou y into dx dy. This is equation 1. Now our aim is to prove f of z dz equal to 0. Integral f of z into dz equal to, see here, f of z is u of x comma y plus I into v of x comma y. This is f of z. Then dz, z equal to x plus iy, dz equal to dx plus I dy. This is dx. Now separate this integral into real and imaginary parts, which is equal to u of x comma y into dx minus v of x comma y into dy. This is our real part. U of x comma y into dx, I into I square minus 1, so minus v of x comma y dy plus I into v of x comma y into dx, then plus u of x comma y into dy. Okay, this is equation number 2. Now compare this equation 2 with our equation 1. Ax dx plus ay dy equal to dou ay by dou x minus dou ax by dou y. That means the second term is differentiated with respect to x minus differentiation of the first term with respect to y. If you approach this first integral in this way, actually this is in the form of u of x comma y dx plus within the bracket minus of v of x comma y close the bracket, into dy. This is actually in the form of u dx plus minus v dy. This is the form actually. Therefore, the second term minus v should be differentiated with respect to x, minus of the first term should be differentiated with respect to y. So if it is the case, this is the first integral is modified as minus dou v by dou x minus, see that, minus dou v by dou x minus dou u by dou y multiplied by dx dy plus I into integral of, here the second term is u, dou u by dou x minus first term is v, dou v by dou y into dx dy. Just I have compared equation 2 with equation 1 and then we have developed this equation. This is f of z dz. Here we have to use surface integral. Yes, not line integral. This is surface integral. Now we have to use our Cauchy-Riemann equation. Dou u by dou x equal to dou v by dou y, then dou v by dou x equal to minus dou u by dou y. These two are CR equations, Cauchy-Riemann conditions present in the complex variables. So this is equation 3. In equation 3 we have to substitute the values. Dou v by dou x equal to minus dou u by dou y. So this is modified as minus dou v by dou x. Instead of this dou u by dou y, once again you have to put minus dou v by dou x. So minus to minus plus, plus dou v by dou x. Entire is multiplied by dx dy plus I into dou u by dou x is our dou v by dou y. So instead of this dou u by dou x, we have to put dou v by dou y. Dou u by dou x should be replaced by dou v by dou y minus dou v by dou y. This is multiplied by dx dy. Now see here, minus dou v by dou x plus dou v by dou x, 0. Dou v by dou y minus dou v by dou y, 0. Therefore, f of z dz value equal to 0. Now we have arrived the condition f of z dz within the integral is equal to 0. Hence we have proved our Cauchy's integral theorem.